In this chapter, we are going to talk about a specific kind of expression called polynomials. And in fact, we have been getting ourselves exposed to certain kind of polynomials before. Let me show you some examples. Let's say we have a 3x minus 5. 3x minus 5 is a linear expression, but this is actually considered as a polynomial, a linear polynomial. Let me give you another example. Let's say we have a 2x squared minus 5x plus 3. This is a quadratic expression, but it is also considered as a polynomial, or more specifically, a quadratic polynomial. So what exactly is a polynomial? Polynomial typically looks like this, where the power of the variable x consists of all non-negative integers. So if you were to look at this, what are the powers of x? To the power of 1 and 5. Is there x? Yes, there is x, because we will see this as x to the power of 0. So we are talking about to the power of 0 to the power of 1. The powers are non-negative integers. And as for this, the powers will be 2, 1, and 0. So the power consists of all non-negative integers. Yeah, this is a polynomial. But if we are looking at an expression that is like this, okay, this is not a polynomial. Why? Because this has a power half, and half is not a non-negative integer. So this expression here is not a polynomial. So I'm using this notation here to represent a polynomial in general, and just to clarify the notation that I'm using, an minus 1, they are not like a power n minus 1. Okay, these are notations to help me to represent coefficient of x. So for example, an will represent the coefficient of x to the power of n. An minus 1 will represent the coefficient of x to the power of n minus 1. So this, I will consider it as a linear polynomial. This, I will consider it as a quadratic polynomial. And very often when we talk about polynomials, we also talk about the degree of the polynomial. And the degree of the polynomial is the highest power of the polynomial. So what is the highest power of this polynomial? 3x minus 5, 1. So this polynomial has a degree of 1. As for this polynomial, it has a degree of 2. And the first thing that I want to try introduce to you guys about polynomial is this property of equality. When we say one expression is equal to another expression for all values of x, what it means is simply any values of x will satisfy this equation. Let me give you a pretty lame example, okay, but it's probably going to help me to put my points across. Let's say we have this equation, x is equal to x. Okay, it is pretty lame, but if you think about it, x is actually all real numbers, right? X, what can x be for this equation? X can be equal to 1, yes, because 1 is going to be equal to 1. If I were to let x be equal to 1, x can be equal to minus 3.5, because minus 3.5 will be equal to minus 3.5. So this equation is true for all values of x. And the moment when one equation is true for all values of x, this equation is called an identity. And I don't want you to misunderstand that, like for example, let me give you an example, okay? Let's say we have a x squared minus x minus 6 is equal to 0. Okay, this is definitely not an identity. Why? Because if I were to try solve for this, it will be x minus 3, x plus 2, this is equal to 0. So x is going to be equal to 3 or x is going to be equal to minus 2. This equation here is true only for two specific values of x. It is not true for all values of x. So this is not an identity. Okay, so not all equations are identities, but the moment when an equation is true for all values of x, then it is considered as an identity. If I were to apply this idea to polynomials, when one polynomial is equal to another polynomial, let's say fx here, is equal to gx for all values of x, then you know what happened? We can actually compare the coefficients of the same powers of x, and they are going to be equal. So for example, if I were to say fx is equal to gx for all values of x, then an is going to be equal to bn, because they share the same powers of x. They are the coefficient of the variable that shares the same power. So an minus 1 is going to be the same as bn minus 1 for x to the power of n minus 1 on both sides of the equation. So it will go on all the way until the very last term, which is x to the power of 0. how can the questions be set for this particular kind of property when it's applied to polynomial? It is usually going to be set when one polynomial is given to you to be equal to another polynomial for all values of x, but within these equations, there are unknown coefficients. And what you're supposed to do is to find ways to solve for these unknown coefficients. And I'm going to suggest two possible methods to solve these questions. I'm going to give you some actual example in a short while. The two possible methods will be to either substitute convenient values of x, or we can also try to compare the coefficients of the same powers of x. Okay, so we have two methods: substituting convenient values or comparing coefficients of the same powers of x. Let me give you an example. Let's say we have this question number 1. Let's take a look at it. So in question number 1 here, we are looking at an expression that is on the left-hand side of this equation, which is 3x cubed plus 10x squared plus 2x plus 27. What is this? This is a polynomial because the powers are all non-negative integer. And this polynomial is equal to another polynomial. I'm hoping that you guys can recognize that on the right hand side it is also going to be a polynomial, in spite the fact that we didn't actually expand this expression. Okay, you can imagine, right? Even if I were to expand this expression on the right hand side, it is going to be consisting of x to the power of n, where n is going to be all non-negative integers. And the question says that this equation here is true for all values of x. And we are supposed to find a, b, and c. And I'm going to use one of the two methods that I've introduced here. So I'll either substitute convenient values of x, or I can also try to compare coefficients of the same powers of x. Let me try to use the first method, which is to substitute convenient values of x. Let me write down the question on the board here. So we have 3x to the power of 3 plus 10x squared plus 22x plus 27. This is equal to x plus 2, ax squared minus x plus 4 plus b of x plus 2 squared plus c. So what are convenient values of x that I can substitute in? And the reason why I can do so is because this is true for all values of x. That is why it gives me the privilege to substitute any values of x in. So what are convenient values? Let me show you one possible convenient values. Okay, the moment when you see it, you know why this number is actually pretty convenient for us to solve for a, b, and c. I'm going to let x be equal to minus 2. Okay, I'm going to let x be equal to minus 2. Can you see why minus 2 is actually a convenient value for me to solve for a, b, or c? Because if I were to let x be equal to minus 2, on the left-hand side, I will definitely be able to just press into the calculator to get a number. But on the right-hand side, this will disappear. This entire expression here will disappear because minus 2 plus 2 is equal to 0. So 0 times anything is still going to be equal to 0. So this expression will disappear. In fact, this will also disappear, right? b times minus 2 plus 2, it is going to be 0. So b times 0, this will disappear, this will disappear. I will only be left with a c. Isn't this very, very convenient for me to solve for c? So this is a convenient values of x that I'm going to try substitute in to solve for one of the unknowns. In this case, it is c. So on the left-hand side, it is going to be 3 times of minus 2 to the power of 3, 10 times of minus 2 squared, 22 times of minus 2 plus 27 is going to be equal to, this will become 0 as discussed. This will also become 0, then plus c. This will give me the value of c to be equal to minus 1. Okay, we are already getting marks here, okay, because we have already solved for one of the unknowns that the question asks for. Can you guys think of any other convenient values of x that can possibly help me to solve a and b fast, because we have already solved for c? I think another convenient value of x that I can think of is 0. I'm going to try let x be equal to 0. Let's see why this value is actually a convenient value, okay? On the left-hand side, this will become 0, 0, 0. So on the left-hand side, I'll be left with just a 27. And on the right-hand side, 0 plus 2, this is going to be 2. And 0 times a, the a will disappear. So I'm going to be left with 0 minus 0 plus 4. So this is going to be 4 plus b times of 0 plus 2 square plus c we have already found out it is equal to minus 1. So now we have an equation that has b as the only unknown. So I can solve for b. b here is going to be equal to 5. Isn't this value convenient? So what we are trying to do here is to try to substitute in convenient values of x. In fact, I don't think there's any more values that are that convenient. But the good news is I've already solved for c and b, which means that to solve for a, I can just sub in any values of x. So let's use the easiest one. How about letting x be equal to 1? I just need to use a value of x that I've never used before. So I'm going to let x be equal to 1. On the left hand side, we have a 3 plus 10 plus 22 plus 27. And on the right hand side, 1 plus 2, this is 3. And we have x is equal to 1. So we have a minus 1 plus 4. And b is equal to 5. So plus 5 times of 1 plus 2, this is 3 square. Then plus c, which is, this is minus 1. This will then help us to solve for a, which is the only unknown. In this case, a is equal to 3. So we have applied the first method to solve for unknowns in this polynomial equation, which is also an identity. Okay, that's why it gives us a chance to substitute in any values of x that we want. The question will actually tell us that this is an identity. So usually I don't think we will be required to spot an identity. Okay, so if any equation is given to you, we will just treat it as any other equation. It is only when the question indicates to you that, hey, this equation is true for all values of x. Like for example, in question number 2 here, this is true for all values of x. Okay, how do I know that this is true for all values of x? Because in question number 2, they actually use a special kind of equal. Okay, and this equal is not an equal with a 2-stroke. This equal is an equal with 3 strokes. Okay, this is not as commonly used in O-levels nowadays. But if you were to happen to see these 3 strokes, okay, it is an indication that this is an equation, yes, but this equation is also an identity. 3 strokes means it is true for all values of x. Let's try to solve for this. Okay, this is true for all values of x. So let's take a look at this question over here. Let me write down the polynomial on the board again. And this time, I'm going to use another strategy to solve for the unknowns. We have just used the strategy of applying convenient values of x. Let's go for another strategy, which is this that I've indicated here in the outline. So the other strategy is to just simply comparing the coefficients of the same powers of x. Okay, so if I were to try to apply that here, we have this x to the power of 4 plus ax to the power of 3 plus 5x squared plus x plus 3 is equal with the 3 strokes. So it is true for all values of x. So this is equal to x squared plus 4 multiplied by x squared minus x plus b plus cx plus d. And since we are trying to compare the coefficients of the same powers of x, so on the left hand side, I think it is fine. On the right hand side, I'm going to try to expand and rearrange this. So on the right hand side, let's try to expand this, okay? So it is going to be this times this. This gives me x to the power of 4. This times this gives me minus x to the power of 3. This times this gives me plus bx squared. This times this plus 4x squared. This times this minus 4x plus 4b, which is this multiplied by this, then plus cx plus d. Let's try to reorganize this expression on the left hand side, because what I want to do is to compare the coefficients of the same powers of x. So I want to congregate all the same powers of x together. So x to the power of 4, there's only 1. So I'm going to leave this as it is. X to the power of 3, it is also just this. So minus x to the power of 3. X to the power of 2, we have this and we have this. So I'm going to group the coefficients together. Factorizing out x squared gives me this as the coefficient. And for x, we have this 2. So I'm going to rewrite this also, grouping the coefficients together. We have this, then plus 4b plus d. Okay, this is also a term that is multiplied to x, except that this is when it is multiplied to x to the power of 0. Okay, so we have one polynomial to be equal to another polynomial for all values of x. We are going to try to solve for a, b, c, and d. So let's do a comparison of the coefficient. If I were to compare the coefficient of x to the power of 3, so comparing, I'm going to be comparing coefficient of x to the power of 3. And if I were to compare the coefficients of x to the power of 3, a is just simply equal to -1. Done. Okay, it is fast. And as for another coefficient that I'm going to compare, I'm going to make use of the coefficient of x squared. So if I were to compare the coefficient of x squared, on the left hand side we have a 5, and on the right hand side we have a b plus 4, x squared, x squared. So this gives me b as 1. And I'm going to compare x and x. So comparing the coefficient of x, on the left hand side it is 1, and on the right hand side we have a c minus 4. This tells me that c is equal to 5. And finally, I'm going to try to compare the coefficient of x to the power of 0. And on the left hand side, x to the power of 0 has a coefficient of 3. And on the right hand side, it has a coefficient of 4b plus d. So this tells me that d is going to be equal to 3 minus 4b. It is 3 minus 4 times of b. b is equal to 1, so d is equal to -1. So this, we have used the second method that I've introduced. It is to try to compare the coefficient. So as for whether you are going to be using method number 1 or method number 2, it really depends on the question. But with more practice, I believe it is actually not so difficult to decide whether method number 1 is better or method number 2 is better. Let me show you another process that is very much related to polynomials. It is this idea of conducting a long division, conducting a division to polynomials. When we talk about division, and if I were to be making use of the notations for division, then for example, we have a 7 divided by 3, let's say. Okay, so if we are looking at 7 divided by 3, I'm going to write it as a fraction. So 7 divided by 3. How do we do a division for this? So if I were to just go back to the basic, 7 divided by 3 is going to be 2 here. 2 times 3 is 6. And I will be left with a 1. So in fact, if I were to look at this and try to re-express this, we can also do that from an improper fraction. We can actually rewrite this into a mixed number. And the mixed number will be 2 plus 1 over 3, or it is 2 and 1 over 3, right? So this is division, and we can actually apply this to polynomials. And please take note that when we are doing this division, it is when we have an improper fraction. So we only do division for improper fraction. When it comes to polynomial, what is considered as improper, this will be considered as improper. This will be considered as an improper expression because, let's look at the degree. Again, what is degree? Degree of a polynomial is the highest power of the polynomial. So the moment when the degree of the numerator is more than or equal to the degree of the denominator, then it is considered as an improper expression that you can actually carry out this process of division. And for polynomial, we call it the long division. Okay, so this that we have here is an improper expression, so we can carry out a long division. Or if I have something that is like this, let's say this minus x plus 5 divided by 4x to the power of 3 minus x squared plus 4x minus 10. Okay, this we cannot carry out a long division because this is proper. The degree of the numerator is less than the degree of the denominator. But if we have something that is like this, let's say this plus 5 divided by 3 minus x plus 5x squared. Okay, this, can we carry out a long division? Yes, we can. Why? Because as long as the degree of the numerator is more than or equal to the degree of the denominator, then that justifies a long division. So how does a long division takes place for polynomial? In fact, it is almost exactly the same idea as this. So let's use this as our reference example, and let's carry out this division over here. Okay, so I'm going to try this division, okay? So we are looking at 6x squared minus 7x minus 1 divided by 2x plus 1. So to re-express this as a division, okay, let's use this as a reference. It is like taking the numerator and I'm going to divide it by the denominator. So we have this. And this times this gives me this, which is going to be minus off from this. For a long division in terms of polynomial, we're going to try to remove the first term. Okay, and to do that, I'm going to multiply this 2x plus 1 by a 3x. If I were to multiply 3x to this times this will give me 6x squared. This times this gives me a plus 3x. And I'll take this expression here minus this expression. Okay, I'm going to be focusing on just these two expressions first. So I'm going to take this, minus away this. This minus this will give me a minus 7x minus 3x gives me a minus 10x. Then minus 1. So I'm going to bring this down. Okay, the next term, I'm going to bring it down. And I'm going to try to remove this minus 10. So to remove this minus 10, I'm going to write a minus 5 here because minus 5 times this is going to give me a minus 10 with the highest power. So minus 5 times 2x gives me minus 10x. Minus 5 times positive 1 gives me minus 5. And if I were to take this expression minus this expression, we're going to be getting a minus 1 minus minus 5 because minus 10 is going to get me a 0. So minus 1 plus 5 gives me a 4. This is how we do a long division for a polynomial over another polynomial. And similarly, we can also rewrite this into the mixed number form. So again, using this as a reference, 2 plus 1 over 3. So it is this expression here, which is going to be 3x minus 5. It is this. Then plus the remainder, which is 4 over this, which is going to be 2x plus 1. We can definitely take this and re-express it further also, because if I were to take this and if I were to just multiply this throughout by the denominator, then this will give me an expression that looks like this. Okay, I will multiply it throughout by the denominator, 2x plus 1. So on the left hand side, I'm going to be left with this, minus 7x minus 1. This is going to be equal to 3x minus 5 multiplied by 2x plus 1 plus 4. This expression here is actually going to be very, very useful. I'm going to be discussing about this next. So in general, this term here, this expression here, okay, this expression here is called the dividend. And then this expression here is called the divisor. And this that is on top, this expression here is called the quotient. And after we have finished our long division, this bottom thing here, it is called the remainder. Remainder, I guess, it is more familiar to us, right? Because we know that the remainder of this is equal to 1. So if I were to re-express it into a form that looks like this, and if I were to call this as fx, then fx is going to be the quotient multiplied by the divisor plus the remainder. So let me just reorganize this a little bit, okay? I'm going to write the divisor, I'm going to write the quotient as q. So qx, then the divisor, I'm going to write it as d. So dx plus the remainder, which gives me this over here. The dividend can actually be re-expressed as the quotient multiplied by the divisor plus the remainder. We actually see this also in here. Okay, it's just that we seldom do this, but if I were to multiply this throughout by 3, then 7 is going to be equal to 2 times 3 plus 1. I mean, it is true, right? 7 is 2 times 3, 6 plus 1. It is 7. So the dividend is equal to the quotient multiplied by the divisor plus the remainder. Because if you can just take note of this, we can actually make use of this to derive two theorems. We are going to look at it in a short while, but let me just show you one more example of long division so that we are a little bit more accustomed to it. Another example that I'm going to try to show you is actually on the next page of the outline. It is here, okay? Please ignore the rest of the information first. Let's just carry out the long division. So I'm going to keep this. Okay, let's do the long division here. So now for this, the long division will require us to take 4x to the power of 3 minus 5x squared minus 7x plus 2. I'm supposed to divide this by x plus 1. Okay, so the long division is there, but let's try to work it out together. So if we were to do a long division, the notation will be this: 4x to the power of 3 minus 5x squared minus 7x plus 2. So we have here a polynomial, right? Because the powers of the variable are all non-negative integers. So this divided by x plus 1. And the first expression that I'm going to focus on will be this here. And I'm going to try to remove the first term in the first expression. So what multiplied by x is going to give me 4x to the power of 3. It will be 4x squared. I'm going to write it above this x squared term. So 4x squared, like how we did it here. If it is x, I'm going to write it above the x term. If it is a term that is independent of x, I'm going to write it above the term that is independent of x. So 4x squared multiplied by this, which 4x squared, I'm writing it above minus 5x squared. So this multiplied by this gives me a 4x to the power of 3. This multiplied by this, it will be plus 4x squared. So I'm going to take this red color underlined expression and minus this away from it. So this minus this, 0. Okay, that's what we are trying to achieve. And this minus this gives me a minus 9x squared. Then I'm going to bring this down, which will give me a minus 7x. So I'm going to think of another expression to be writing above this minus 7x. So it is going to be also multiplied to x. And that should help me to remove this minus 9x squared. And I guess minus 9x is going to do the job, because minus 9 times this gives me a minus 9x squared. Minus 9 times this gives me a minus 9x. So if I were to take this, minus 9x squared will disappear, and minus 7x minus minus becomes plus. So minus 7x plus 9x gives me a 2x, and this I'm going to bring it down, and I'm going to find a term that will be multiplied by this so that I can remove this 2x. So this is going to be, I guess 2 will be good. So 2 multiplied by x gives me 2x. 2 multiplied by 1 gives me positive 1, and this gives me a positive 2, and this minus this gives me 0. Which means if I were to try to re-express it into the form of this, then we have 4x to the power of 3 minus 5x squared minus 7x plus 2. This can be expressed as 4x squared minus 9x plus 2 multiplied by the divisor, which is x plus 1, then plus the remainder, which happens to be 0. Okay, this is about long division. So let me now focus on this. Okay, and we're going to derive two very, very useful theorems for this. This is going to be tested quite a lot in our exam, so let's pay attention to this. Okay, I'm going to go back to the second page of the outline. So we're going to be focusing on this division theorem. Okay, and we are going to start off by coming back to this equation over here. So let me rewrite this equation. So from what we have derived, we know that fx, this can be written in terms of its quotient, its divisor, and the remainder. And if I were to just rearrange it a little bit differently, then I'm going to write this as the divisor first, multiplied by its quotient, plus the remainder. Okay? In general, when we carry out a long division, or even if it is a usual kind of division, you realize that the remainder will always be smaller than the divisor, correct? Because when we were trying to do this, then we are dividing it by, just now what we did, it was to be dividing this by 3, so it's 2, 6 minus 1. So when we get a number here, a number here that is less than the divisor, we know that this is where the division is going to stop. It is the same for polynomial. When you're trying to do this division, and the moment when you realize that the expression here is a polynomial that is at least 1 degree less than the divisor, that is when things are going to stop. So that was what that happened here. Okay, when we did our long division, how do we know that we are supposed to stop here? Because this is 1 degree less than the divisor. Okay, I've tried to write it down here. Okay, the same goes for this that we did just now. When we carry out the long division and we get a constant is 1 degree less than the divisor, because the degree of the divisor here is 1 and the degree of a constant is 0 because it is x to the power of 0. So if I were to just try to re-express it in terms of this, will the remainder be an expression that has x? Yes, it is possible. Why? That is usually when the divisor is maybe something that is like quadratic. Okay, let me give you an example. So let's say when I do a long division, let's say this is x to the power of 4 and so on. Okay, so x to the power of 4, then the rest of the terms where the powers of x are non-positive integer will give me a polynomial. And if I were to divide this by x squared and so on, okay, I'll get a quotient. And what do you expect for the denominator, for the remainder? The remainder should be 1 degree less than the divisor. So I'll be expecting a remainder that looks like either this, which is a linear expression, a linear polynomial. So the degree is 1 less than the divisor, which is 2. Or it can also turn out to be just a constant. So it can be either this or it can also be this, either of this. Okay, as long as the remainder is at least 1 degree less than the divisor, then that is when the whole long division is going to stop. And that is when this expression here, okay, this expression, okay, as long as this expression that is here, you're getting one that is at least 1 degree less than the divisor, then that is when you know that you have reached the final part of your long division, and that represents for us the remainder. That is why for this remainder here, I'm also writing as a function with respect to x. Rx. Okay, I'm not writing it as just R. Okay, previously we just used an R because in the example that we did previously, it was like just a constant. Okay, but we know that it may not be so in general, so we're going to stick to this. But if the divisor happened to be a linear expression, so for example, if the divisor happened to be something that is like this, then I know that the remainder here will just be a constant because the degree is 1. And here it must be at least 1 less than the degree of the divisor, so it must be a constant. Okay, so if the divisor happen to be linear, for example, if dx is ax minus b, then the remainder is going to be a constant. So I'm going to re-express this equation that I've written on the board as something that is closer to what we are going to be learning in our syllabus, because for our syllabus, we will usually be analyzing a division scenario, a polynomial scenario, where the divisor is a linear expression. So if I were to let d be a linear expression, for example, if I were to let d be ax minus b, then we will have a fx to be equal to ax minus b times qx plus a remainder, which is actually going to be 1 degree, at least 1 degree less than the divisor. So I'm going to use r, which gives me this that is in the yellow color box. I do think that this is even more important than this, although this is a general form that we are expecting when we try to divide a when we try to carry out a long division for a polynomial. But if the divisor happen to be linear, then let's go for this expression instead. And this expression here, this one here, okay, so let me remove this. Although this is still good, but it is just not as often asked in our syllabus. Okay, so let's look at the first theorem that we can derive from this. The first theorem is the remainder theorem. It is actually very, very easy. That means even without carrying out a long division, you're actually able to just find the remainder if the divisor happens to be a linear expression. Okay, we are talking about specifically the case where the divisor is the linear expression. Okay, so let's not forget that this is the divisor, so dx. So how do we find the remainder without having to even go through the long division? I mean, long division, it is going to be a tedious process, right? So if we have remainder theorem, we can actually skip that process and find the remainder directly. You know what I'm going to be applying? I'm going to be applying substitution of convenient values of x. That was what we did just now. We're going to try to substitute convenient values of x, because if this polynomial is equal to this polynomial for all values of x, which it does, because we are just re-expressing 7 is equal to 2 times 3 plus 1. It is equal to for all values. If I were to apply that to polynomial, it is true for all values of x. It is just re-expressing something. It's like 2x is equal to x plus x. Okay, so this is true for all values of x. And if I'm supposed to find the remainder, which is r, okay, we have done this before, because in the previous part we have talked about this, right? Substituting convenient values of x. So if I were to apply that to this scenario here, and my aim is to find r. My aim is to find r. What is the convenient value of x that we are going to be using? We are going to use a value of x that will cause this to be 0. So if I were to let ax minus b to be equal to 0, x is going to be equal to b over a. And this is a convenient values of x that I'm going to apply to find the remainder, because if I were to let x be equal to b over a, we can just do a bit of mental sum. By letting this be equal to 0, x is equal to b over a. So if I were to let x be equal to b over a, that means on the left hand side we will have a f b over a, and on the right hand side it is going to be a times of b over a minus b times the quotient, which I don't exactly know what it is because I didn't carry out the process of long division, but it doesn't really matter now because this is going to be equal to 0. A and a can be cancelled, right? A and a here can be cancelled. We're going to have b minus b, it is equal to 0. I mean, obviously it's going to be 0 because that's how I derive the value of x, by letting this ax minus b be equal to 0. So this leaves me with a f b over a is equal to 0 plus r, and this is the remainder theorem. So if you have a polynomial and you want to divide it by a linear expression without having to go through the long division, the remainder will just be the value of x that caused the linear expression to be 0. It will be the value of x that caused the linear expression to be 0, the remainder theorem. And what if the remainder is equal to 0? If the remainder is equal to 0, let me give you a numerical example of a division case, okay? So let's say if I were to take 6 divided by, let's say 3. 6 divided by 3. 3 is actually a factor of 6, right? So this is 2. 2 times 6, this is going to be 6 minus, this is 0. Let me give you another scenario. Let's say I have 8, divide this by 2. So we have a 4, then this will be 8 minus 0. So what is in common between these two? The remainder will be 0, which means that if we were to be dividing something by its factor, then we will be expecting 0 to be the remainder. It is this that I'm trying to mention here in the factor theorem. Okay, it is an extension of the remainder theorem, except if ax minus b is a factor, then the remainder, which is f b over a, this is equal to 0. Okay, if it is a factor, this is equal to 0. But even more, the idea that is even more applicable to us in our syllabus will be this. What if we are able to check and we realize that fb over a is equal to 0? That means the remainder is equal to 0. And that means the value of x that will cause fx to be equal to 0 is b over a. So in this case here, x is equal to b over a. And if I were to just reverse back the process, this gives me ax minus b is equal to 0. And this gives me a factor. The factor theorem helps me to achieve this. If I were to realize that fb over a is equal to 0, then this tells me that ax minus b is a factor. of the function fx, and fx has to be a polynomial. Remainder theorem, factor theorem. They are very, very useful theorems that can help us to process polynomial by skipping certain processes, like for example, the long division. Let's take a look at some examples. Let's take a look at these two parts of the question. Okay, they will give us good examples of how this remainder theorem and factor theorem are going to be carried out. So for this question, we have in part A an expression that is given to me, 2x to the power 7 minus 6x to the power 5 plus ax to the power 4. This is a polynomial. Okay, and it leaves a remainder of minus 4 when it is divided by x plus 1. We are supposed to determine the value of a. The first thing that I'm going to do is I'm going to try to relate this back to the remainder and factor theorem. Okay, so we're going to try to relate it back to this. Okay, and specifically, I'm going to use the remainder theorem. So again, if fx is divided by ax minus b, then the remainder is f of the value of x that will cause this to be 0, which is b over a. Okay, but just by letting this be equal to 0, x is b over a, and that will help us to get a value for this. So if I were to apply this to this question here, we are going to let fx be equal to 2x to the power of 7 minus 6x to the power of 5 plus ax to the power of 4. It leaves a remainder of minus 4 when it is divided by x plus 1, which means that f minus 1 is going to be equal to minus 4. Right? The remainder is going to be equal to is going to be equal to the function where the value of x is going to be the value of x that caused the divisor to be equal to 0. Okay, so I'm applying this here. Okay, the remainder is going to be f of minus 1 when this is divided by x plus 1. Let me write down x plus 1. So this is x plus 1, which means that this can also be expressed as the divisor multiplied by the quotient plus the remainder. So if we were to let x be equal to minus 1, which is a convenient value of x, it is going to cause this to be equal to 0. So if fx is equal to this, when I let x be equal to minus 1, on the left hand side, it is just going to be f minus 1. And on the right hand side, this will disappear. This will give me the remainder. So according to what this question says, the remainder is equal to minus 4 when it is divided by x plus 1. We're going to just simply apply the remainder theorem. So if I were to apply the remainder theorem, f minus 1 will be 2 of minus 1 to the power 7 minus 6 minus 1 to the power 5. A here minus 1 to the power 4. This is equal to minus 4. This will help me to solve for a. A in this case is equal to minus 8. And hence, the question says, hence we are supposed to find the remainder when the expression is divided by x minus 2. So now we know what exactly is fx. Fx is equal to 2x to the power 7 minus 6x to the power 5. A is minus 8. So minus 8x to the power of 4. What is the remainder? The remainder, by applying the remainder theorem, the remainder will just be f of 2. Okay, because this is supposed to be divided by x minus 2. So by letting x minus 2 be equal to 0, x is equal to 2. And by substituting this value of x back into the function, this will straight away give me the remainder. Okay, so when this is divided by x minus 2, the remainder is f2. And this is equal to 2 times of 2 to the power 7 minus 6 times of 2 to the power 5, 8 times of 2 to the power of 4. The remainder, if I were to just press this into the calculator, is minus 64. Next, in part B. In part B, we have another expression. So let me use another function to represent this other expression. And I'm going to go for g. So I'm going to let gx be equal to x to the power of 3 plus px squared plus qx minus 2. And p and q are constants, so they are the coefficients, and it has a factor of x minus 2. it has a factor of x minus 2, and it has a remainder of 25 when it is divided by x plus 3. So let's make use of the first piece of information. It has a factor of x minus 2. I'm going to make use of the factor theorem. So if it has a factor of x minus 2, that means g of 2, this is going to be equal to the remainder, which is 0. This is using the factor theorem because x minus 2 is the factor. So g2 is equal to the remainder, which is 0, because I'm dividing it by a factor. So this is the first piece of information, and the second piece of information is that the remainder is 25 when it is divided by x plus 3, which means that g of minus 3, x plus 3, if I were to let x plus 3 be equal to 0, x is equal to minus 3. So g of minus 3 is equal to, according to the question, the remainder is 25. I'm using the remainder theorem. G of minus 3 is equal to 25. So for this, we can come up with our first equation. If I were to substitute 2 into here, we have a 2 to the power of 3 plus p times of 2 square, q times of 2 minus 2, this is equal to 0. This gives us our first equation, 2p plus q, this is equal to minus 3. This is our first equation. As for this, I'm going to let x be equal to minus 3. So minus 3 to the power of 3 plus p minus 3 square plus q of minus 3 minus 2, this is equal to 25. Our second equation looks like this. 3p minus q is equal to 18. Equation number 2. And we can actually solve this simultaneous equation very, very easily. I'm going to take equation number 1 plus equation number 2. So 2p plus 3p, we have a 5p. And q minus q is going to get me a 0. Minus 3 plus 18, this gives me a 15. This tells me that p here is equal to 3. And then I'm going to substitute p is equal to 3 into, let's say, equation number 1. So we have a 2p, p is equal to 3, so 2 times 3 plus q, this is equal to minus 3. This will help me to solve for q. Q in this case is equal to minus 9. So this is the application of the remainder theorem and the factor theorem. But one of the most useful parts of the remainder and the factor theorem, specifically the factor theorem, is to solve questions that is like this. Let me show you the last thing that I want to talk about. It is when I try to solve a polynomial in general. Have we solved polynomials before? Yes, but we have concentrated on solving linear polynomial and quadratic polynomial. But what if it is to the power of 3, x to the power of 3, x to the power of 4? So for this kind of polynomial where the degree is 3 and above, we have actually never learned how to solve them. For the linear polynomial, we'll just rearrange to make x a subject. For a quadratic polynomial, we'll usually just either factorize, or we can complete square, or we can make use of the quadratic formula. So now we are going to look at what if it is x to the power of 3, what if it is x to the power of 4. What can we do to solve this kind of polynomial? So let's take a look at this particular example over here. And in this example, we are supposed to solve this polynomial. 4x to the power of 3 plus 2 is equal to 5x squared plus 7x. Solving for polynomial is pretty consistent regardless of whether it is to the power of 3 or to the power of 2. So if I were to solve a polynomial that is to the power of 2, okay, let me give you an example also. So let's say I have this x squared minus x is equal to 6. Solve this polynomial, solve this quadratic equation. Okay, but now we know that it is a polynomial. So how do we solve this equation? Okay, I'm going to bring everything over to one side. Then I will factorize it. Then this tells me that x minus 3 must be equal to 0, so x must be equal to 3. Or x plus 2 must be equal to 0, so x is equal to minus 2. So this is the process that we have been using to solve a quadratic polynomial. And I'm going to try to import and apply this to a cubic polynomial that we are seeing here. And it is also applicable to a quartic polynomial, which is to the power of 4 and so on. So the first thing that we are going to do is we are going to try to re-express this, step 1. Let's try to re-express this so that one side of the polynomial is equal to 0. So I'm going to shift everything over to the left-hand side. Minus 5x squared minus 7x plus 2. This is equal to 0, step 1. And I'm going to just let the expression that is on the non-zero side be equal to a function. In this case, I'm going to go for fx. So I'm going to let fx here be equal to 4x to the power 3 minus 5x squared minus 7x plus 2. And usually when such questions appear in the exam, the question will require you to show the full set of solution. Although maybe some of you already know this, we can actually make use of our calculator to solve for a polynomial that is like this. Okay, let me show you how we can do that. So if I were to just use my calculator, and I'm going to go to equation, so number 3. And this is a cubic polynomial, so it is going to be x to the power 3, so I'm going to choose here number 4. And here we're going to press in all the coefficients. The coefficients will be 4, minus 5, minus 7, 2. So I'm going to press in 4. Okay, I'm going to press in 4, I'm going to press in minus 5. I'm going to press in minus 7. And I'm going to press in 2. Okay, so if I were to let the calculator solve for it, I will have 2 as the root, 1/4 as the root, and minus 1 as the root. Which means that just by pressing the calculator, x is going to be equal to 2, or x is going to be equal to 1/4, or x is going to be equal to minus 1. This is from our calculator. But when you try to present this as part of your solution, we have to explain that we are not exactly using the calculator, because what you are expected to do is to use a bit of guessing and checking to verify the first root of the polynomial. So when it comes to presenting this in our solution, we are going to give an indication that we have actually done some testing. Okay, so what I wrote here, by trial and error, I'm guessing that maybe x is equal to minus 1 is a root. I can also definitely make use of 2. Okay, but I think I'm going to skip using 1/4, because 1/4 just doesn't seem convincing that it is a number that I've guessed, right? So I can use 2, I can use minus 1. So by trial and error, I know that f minus 1, okay, if f minus 1, that means it is going to be 4 times minus 1 to the power 3 minus 5 times minus 1 to the power 2 minus 7 times minus 1 plus 2. And if you were to evaluate it, this is equal to 0. You know why it is important for us to find a root? Because a root, when it is being substituted back, fx is going to give me a 0. And what do we know about fx is equal to 0? The value of x. If f of a number is equal to 0, then this number actually gives me a hint of what exactly is a factor of this polynomial. So if f of minus 1 is equal to 0, then this indicates to me that x is equal to minus 1. That means x plus 1 is going to be a factor. So when I manage to find something that is like this, then I can actually say that therefore x plus 1. Okay, when minus 1 is a root, then according to the factor theorem, x plus 1 is a factor of the polynomial fx. Okay, but in case you are just thinking, okay, that means without using a calculator, I really have to do random guesses. Is it so? Okay, I mean, I'll definitely try to press in the calculator to get the numbers first, but what if I really cannot depend on a calculator? Okay, then is there any way that I can guess a number that is here, but it is not that random? Okay, or else there are so many numbers for us to be guessing, right? There's a very logical process that we can make use of to reduce the number of values that I can substitute here to do my trial and error, to do my guess and check. And those numbers can be inspired by, if you were to look at a polynomial, it is actually very logical. Okay, it can be inspired by this here, this 2 here. Let me explain to you why it can be inspired by this 2. Because we are trying to re-express this into its factor. Okay, re-express this into its factor. Why do we want to do so? Because that was how we have solved for polynomial all along. We want to re-express it into its factors. And hopefully they are linear factors. So this is to the power of 3. How many factors will you be expecting? You'll be expecting 3 factors, because it is going to give you 3 roots. So every root is going to give you a factor. So this will be expecting 3 factors, something times something times something. Okay, like this, to the power of 2, we're expecting 2 factors, this times this. And you know, for this, it is going to be something that is like ax plus some number, then bx plus some number, then cx plus some numbers. But do you realize logically, if I were to get my inspiration from this term, this is the term that is independent of x. If I were to expand this, how will I get a term that is independent of x? It must be this term, which is a constant, multiplied by this term, which is also another constant, and multiplied by this other term here, which is also a constant. So this multiplied by this should be giving me a 2. Right? Okay, we must be, you must process this together with me, okay, because we are trying to use a logical deduction. Which means that if I were to look at 2, and I try to break it up into its nice factors. 2, if I were to break up into its factors, it can be plus or minus 1 or plus or minus 2. And these are the few numbers that may be occupying this position, or this position. Plus or minus 1, plus or minus 2. And these are the numbers that if I really have to make use of to guess, okay, without having my calculator with me, okay, if I really have to guess, this is where I'm going to get my inspiration. I'm going to take a look at the term that is independent of x, and I'm going to ask myself what are the factors, and one of the factors I'm going to just test. If I get a 0, then yes, I will get the factor of the polynomial. If not, I'm going to try another one. Okay, and this is very useful so that we can boil down the number of values that we are going to try substitute. Or else, if it is truly a trial and error, if it is truly a guess and check part, without getting inspiration from my calculator, without the help of my calculator, we can't be really substituting every possible value. Okay, and can you see this minus 1 that I've used is actually this. Okay, so if we have gone through this process here, which is my step 2, which you can find a term to substitute to find out whether it is going to be a root, which can subsequently give you the factor. We can go for either of these 2 methods. One is to make use of our calculator. The other one is to try to look at the term that is independent of x, which is 2 over here. Okay, and break it down into its factors, and one of the factor should probably give you a 0 when you're substituting it back into f. Okay, so now we have a factor, and what we want to do next is to find the rest of the factors. And because it is to the power of 3, we are dealing with polynomial with degree 3, degree 4, and so on. So the other factors are not going to be that straightforward. And what I'm going to do next is to do a long division to get the other factor. So I'm going to do a long division. In this case, I'm going to take this fx, which is 4x to the power of 3 minus 5x squared minus 7x plus 2, and I'm going to divide it by x plus 1. We have done this long division a short while ago, right? So it is the same process. If we were to do a long division, we are going to be getting a 4x squared minus 9x plus 2, and because we are dividing this by its factor, so what do we expect here? We expect that we are going to end up with a remainder that is 0. This 0 is good for us to check that we have done our long division correctly, to check that I have found my factor correctly. Okay, because I'm dividing this by its factor. And if I've done anything that is wrong, I may not actually be getting a 0 here. So I know something is not correct. Okay, so that will prompt me to continue with the rest of the check. So if I were to do a long division in this way, then I can conclude that step number 4, fx is going to be a multiplication of its factor, which is going to be x plus 1 multiplied by 4x squared minus 9x plus 2. Or if you can actually remember what we have discussed previously, fx after a long division process, let's just take a look at it. After a long division process, fx is going to be rewritten as the divisor multiplied by the quotient plus the remainder, and in this case is 0. Okay, so we have talked about it here. Okay, the quotient multiplied by the divisor plus the remainder, but of course this is a factor, so it's just this multiplied by this. And once you have managed to factorize this, you will try to factorize it even further because this can be factorized, right? This is a quadratic expression, so you can factorize it as per how you factorize all the other quadratic expression. But in case this happen to be a cubic expression, okay, for example, this is to the power of 4. So if I have a linear expression here, then we will be expecting a cubic expression here. So if it is a cubic expression, you may have to go through this whole process again in order for you to factorize it further. If not, in this case here, we can factorize it to 4x minus 1 and x minus 2. And then the last step, step number 5, I'm going to replace fx. I'm going to replace fx here by this expression. So therefore, if fx is equal to 0, then I can say that x plus 1, 4x minus 1, and x minus 2, this is equal to 0. And from here, just like what we have done here, that means x plus 1 is going to be equal to 0, or 4x minus 1 is going to be equal to 0, or x minus 2 is equal to 0. So this gives me x is equal to minus 1, or x is equal to 1/4, or x is equal to 2, which are the same values that we have obtained when we try to solve it using our calculator. But before I end, let me just tell you another trick that we can probably make use of instead of doing a long division. Long division is good. It is a very, very stable process, but it may not be the fastest all the time. So I'm going to introduce you to another strategy which may or may not work. Okay, in case it didn't work for that particular kind of question, then what I suggest that you do is you switch back to long division. But it is going to work for here, and you'll probably see the logic why. So what I'm going to do is, I'm going to try to do a comparison of the coefficient. Okay, to do this, we need to make some assumption. So let me give you an example. Since I know fx is going to be, a function, a polynomial that has a factor of x plus 1. So I can also re-express fx, which is equal to this, 4x to the power of 3 minus 5x squared minus 7x plus 2 as x plus 1, this is the factor, multiplied by its other factor, which at this moment I'm still unsure what that factor is. So, but I know that this other factor here should be a quadratic polynomial. Why do I know that? Because this is cubic and this is linear. So this must be multiplied by something that has x to the power of 2 in order for the ultimate expansion to have an x to the power of 3, right? So I'm going to assume this to be, for example, ax squared plus bx plus c. I'm assuming this quadratic expression here to be one that is of a form that is like this, where the coefficients a, b, c are what I plan to try solve. So for a, b, c, how am I going to solve this? I'm going to solve this by comparing coefficient. So if let's say I'm going to try to compare the coefficient of x to the power of 3. On the left hand side, it is equal to 4. And on the right hand side, how am I going to be getting an x to the power of 3? It is going to be x multiplied by x squared. So what is the coefficient? 1 multiplied by a is a. So I've managed to solve for a. If I were to next go for the coefficient of x to the power of 2. X to the power of 2 on the left hand side, it is minus 5. And on the right hand side, x to the power 2, okay? So this multiplied by this is going to give me x to the power 2, so we have a b. And this multiplied by this will give me x to the power 2, so we have a plus a. And that's it. On the right hand side, if I were to expand, these are the only two terms that will give me x to the power 2, which means that minus 5 is going to be equal to b plus a, which is 4. This tells me that b is equal to minus 9. And the last one that I'm going to try to compare is x to the power of 0. So for x to the power of 0, on the left hand side it is 2. And on the right hand side, to get x to the power of 0, it is going to be 1 multiplied by c. Okay, because for the rest of the terms, I'm going to be having a variable x to the power of at least 1. So 1 multiplied by c is going to give me x to the power of 0, which is going to be compared to this. So this tells me that c is equal to 2. So what is this other factor? This other factor, which is a quadratic factor. This quadratic factor here is equal to, this quadratic factor is going to be equal to a, which is 4. So 4x squared plus bb is minus 9 So this plus c, c is going to be equal to 2, which is exactly the same as this, which we have obtained using the long division. And that's all I have for my chapter here. And I hope you can understand the polynomial better through my explanation to you. And I'll see you in my next chapter.